In this episode of Single Variable Madness, we have to find all the prime numbers in the form n to the power of 4 plus 4, where n is a natural number. So 1, 2, 3, 4, 5, and so on and so forth. So let's start with this expression, n to the fourth plus 4. If we can factor this in a way where it can show us if when plugging in a certain natural number it will give us a prime or not, that will be really helpful. So we have to find out how to factor n to the fourth plus 4. And the way that you can factor expressions like these, where at first it seems unfactorable, is to introduce a new term. So for instance, if we introduce, so it's n to the fourth, if we introduce a plus 4n squared plus 4, then suddenly this expression becomes factorable. It can be factored into n squared plus 2 whole squared. So we introduce this plus 4n squared. However, we can't just add this term in. We have to subtract it as well in order to balance it out. So let's factor this whole thing. And by this whole thing, I mean these three terms. Let's ignore this minus 4n squared for now, but if we factor n to the fourth plus 4n squared plus 4, we get n squared plus 2 whole squared. If you factor again the first three terms, you get this, and then subtract 4n squared. So now what? Did that do anything helpful in this scenario? Yes. Now we have a difference of 2 squares, as you can see over here. This over here, n squared plus 2, is getting whole squared, and this 4n squared can be also written as, I'll just write it on top, 2n whole squared. So let me just write it again. So again, you have n squared plus 2 whole squared minus 2n whole squared. So now that we have this difference of squares, we can now use the identity that a squared minus b squared equals a plus b times a minus b. So let's rewrite this as, in this case, a is n squared plus 2 and b is 2n. So a plus b would be n squared plus 2n plus 2. I just wrote the 2n in the middle of n squared and 2 just to make it look more like a normal polynomial. And then this is a plus b, and then a minus b is n squared minus 2n plus 2. So just like that, we factored n to the fourth plus 4 into n squared plus 2n plus 2 times n squared minus 2n plus 2. So what help do we have now? Like, what benefit is this to us? Well, now let's just try to plug in n equals 1. Again, the natural numbers are 1, 2, 3, 4, and so on and so forth. So plugging in n equals 1, let me just write over here, n equals 1 gets us, let's see, plugging into here gets 1 plus 2 plus 2, so that's 5. And over here, it's 1 minus 2 plus 2, so that's 1. And that gives us 5. 5 is prime, so that is that's one prime number that fits this constraint. However, if we go on to n equals 2, I don't even have to write what the answer will be, because now with n equals 2, both of these values are going to be positive. It's going to be some positive number times some other positive number. And both of these are going to be numbers that are greater than 1. Because n squared minus 2n plus 2, yeah, when you plug in n equals 1, you're going to get a value of 1. But when you plug in a value greater than 1, now you're going to get a value bigger than 1. And so it will be a positive number greater than 1 here, and a positive number greater than 1 here. So that means it will always be a composite number. Again, now, after you plug in n equals some natural number greater than 1, you're always going to get a composite number, because you're going to get some positive number greater than 1 here and some positive number greater than 1 here. And a prime number cannot be the product of two numbers greater than 1. Therefore, we can say that the only prime number in the form n to the fourth plus 4, where n is a natural number, is 5. And we are done.